my name is Ryan Warba. I'm going to be presenting the identifier robot. This robot is named the identifier because it identifies where the potholes are and it sends coordinates and information to the other robots so that they can fill those potholes and repair them. Alright, so let's talk about the mechanical design of the robot. It'll check for potholes, and if there is a pothole, then it'll do a serial.write line. And the reason it does this is because we need the other robots to read that information. And so the main purpose of this robot is to check for those potholes, send the information to the other robots. And you'll see here on the bottom right in the diagrams, we obviously have wheels. I mean, we need wheels, right? The red bulbs are distance sensors, so we need to tell how far things are so that the robot can traverse the environment. And the distance sensors are especially on the bottom because it will drive over potholes and use that information in order to identify where a pothole is. Lastly, we have the Arduino hatch. Any electrical components can go into the hatch, but I needed a place to put them, so there's a hatch there. Alright, next we're going to talk about the electrical design. So here we have a distance sensor that is reading information. You can imagine when a robot rolls over a pothole, it will basically tell how far down the pothole goes, how deep it is, and we send that information to the other robots, which is very important. There's also a motor that's hooked up to all this, and the reason for the motor being there is if there's a case where there's a curb or something where the wheels have to do more than just turning, the motor can be used for that, and the motor might also be used for the hatch or other components. Alright, let's talk about the software design of the identifier robot. You'll see in the code that it says if the distance is less than 5 inches that it will power down the motor. The reason this is happening is because you can imagine when a robot rolls over a pothole and it's deep, the distance is going to be much greater than 5. So we want to turn the motors on and send information and write information when we realize that there is a depth change that goes further than what the road would normally be in height to the robot's sensors. So that's why that's there. That just about wraps it up. The only other difference is with this robot in particular, when the motor is on, it will send information, and when the motor is off, it will not. So it's very important that the distance sensor and the motor work together, which was shown before.
Hello everyone, my name is Mo and I'm here to introduce the pre-filler robot, which is a key player in the pothole repair swarm. The pre-filler robot prepares potholes for optimal filling and leveling by its fellow robots in the swarm. So let's explore the mechanics of the pre-filler robot. Over here we have the tracked platform which provides stability on uneven ground. We also have a hydraulic hammer with a chisel attachment that is to ensure clean edge trimming and eliminate any extra tools. And we also have the rotating wire brush which efficiently removes debris and prepares the pothole for a perfect repair. As safety is crucial, we have ultrasonic distance sensors that are placed all around the robot which constantly scan for obstacles. It is equipped with a gear motor for a smooth movement of the tracks, a DC motor for the rotating wire brush, and the hydraulic hammer is driven by a microservo motor. Here we have the electrical design for the pre-filler robot. For the microcontroller, we have the Arduino Uno drive hooked up to our breadboard, alongside wired with the 4 distance sensors and our 3 motors, powered by the 9-volt battery. Here we have the sign and a snippet of code where we have the setup function and also the loop function. Setup function, basically we put up the pins to control the motor and to turn on the communication, and the loop function is for the sensors to check for obstacles and receive command via the serial communication and takes action accordingly. On this snippet of code we have the commands that we set up with, and on our last slide we have the flowchart which shows the pre-filler robot begin its loop, use metasensors to scan around for any obstacles, In case there's an obstacle, it will halt the robot, sending a halt message, and then it will loop back to start the loop from the very beginning. If there's no obstacles, then it will wait for a command, and it will either process the command or not. Here we have the simulation. Let's start the simulation. And if we put F, it should move forward as we see 30 RPM. Put B, it will go to negative 30 RPM. And if we push X, brush motor will start at 12 RPMs. And if we push Y, go back to 0. N will move the hammer and chisel motor. And S will stop it.
Good afternoon, everyone. My name is Sarah Malloy, and today I'll be sharing the Tamper robot with everyone. It is the final robot in the pothole repair process. Its job is to identify the newly filled pothole and tamper down the material using a hydraulic press with a steel plate attached. The robot is equipped with motion sensors, pressure sensors, and level sensors to properly tamp down the newly laid road material. The goal of this robot is to properly pack down the road material in a manner that maximizes the life of the repair, thus saving resources in the long run. First, we're going to take a look at the mechanical design, which is made up of 4 major components. The first being the all-terrain wheels to ensure the robot is able to traverse smoothly without worry of getting stuck. Next, we have the steel plate. This guarantees to tamp down the road material firmly and level. After that, we have our hydraulic system. This includes the pressure sensor, oil reserve, hydraulic lines, relief valve, and the hydraulic press, which work together to move the steel plate. And then lastly, we have the DC motor, and it is used to sense when to start and stop the hydraulic system. Now we'll take a look at the electrical design. This will sense when the robot is above the target area and will start the DC motor. Once the DC motor is started, this will relay information to the hydraulic system, which will then begin the tamping sequence. Once the tamping sequence is complete, the motor will shut off and the information will be relayed back to the control panel. Now we'll go over the actual code. The code shown is for the initiation and the completion of the tamping sequence. The code sets up the parameters for the duration of the sequence as 2 minutes and the required information for the for loop. The for loop is how the tamping sequence knows when to start. When the robot is within 30 centimeters of the pothole, the DC motor will start, which will actuate the hydraulic tamping sequence. After 2 minutes of the tamping sequence, the motor will automatically turn off and the loop will be complete. The loop will not begin until the robot is within 30 centimeters to ensure the robot is placed properly. Lastly, we'll look at the flow chart for the tamping sequence. The robot will begin searching the pre-programmed area for any newly filled potholes. Once the robot is within 30 centimeters of the pothole, the 2-minute tamping sequence will begin. Once that sequence is complete, it'll continue searching for the next pothole. If the robot is not within 30 centimeters of the pothole, it will continue to look for any newly filled potholes until it completes the pre-programmed amount of tamping cycles. And that is it for the tamping robot. Thank you so much for listening.
My name is Jonathan Jatombliansky. I'm the creator of the Robo Filler, which aims to bring the filling material to cover the pothole within the pre-designed working area and specifically to the pothole identified by the identifier robot. The design consists of a steel base where all components are placed, including the wheels and a bed with a mechanical arm operated by a gear motor and a cog which pushes the filling material from the back of the bed, activated by a depth sensor at the bottom of the robot, which is facing down. The robot also has a front-facing distance sensor, which serves the purpose of navigating the robot to a preset working area. It also has 2 blinking LEDs right and left to differentiate the commute from the working mode when operating. On this slide, you can see the Arduino Uno electrical setup with all the components, including front-facing and depth sensor, wheels, gear motors, and arm gear motor. In working mode, you can see that the code activates the wheels moving forward, and when the depth sensor identifies the depth above 3 inches, the arm motor is activated, pushing the filling material out of the top bed. To conclude, here's the diagram explaining the logic behind the commute and the work mode, and back to base to refill the bed if and when needed. Next is the collective behavior by Ryan Borba.
All right, everyone, this is Ryan Borba. I'm here back again with collective behavior this time. We're going to be talking about how all the robots behave together. Now, there are two parts to this. There's local sensing and communication, and there's the feedback and the action. So in the local sensing and communication part, we're talking about the sensors and actuators that the robots have to talk to one another through a hub. And the feedback and action is where the central hub is acting to send information to and from robots. So let's look at the diagram here. I'm going to zoom in so it's actually readable. We start off with the robots being deployed. After that, my robot, the identifier robot, goes in and it collects data on pothole dimensions, and then it leaves when it's done. Pothole dimensions are sent to the central hub, and if we try to go right here, it asks if the prefiller has finished, which it has not. We haven't done anything with the prefiller yet. So we're going to send data to the prefiller robot to set up an area for the filler robot. So the prefiller robot is just setting up the area, it's prepping it. We ask if the prefiller is done. If it is not, it goes back and does its work some more. But if it is done, it goes back to the hub. The hub takes that information and says, okay, prefiller is finished now. So the filler robot enters and does its job, filling potholes, and using data from the hub to do that. Still using data we got all the way from the identifier robot. After that, we ask, is this robot finished? Has the filler robot finished its job? If it has not, it goes back and continues, and if it is done, then the filler robot leaves and the tamper robot comes in to stamp the area down and flatten the material that was just filling the pothole, or the pothole material that is in the pothole now because it's been filled. We ask if the tamper robot has finished its job. If it has, then all the robots drive back to their headquarters and this system finishes. If the tamper robot has not finished, again, we just go back and have it do its job. Ooh, that was a lot. So that's the idea of that diagram and how the robots talk to each other. It's through a hub system. The hub sends data all the way through the entire system, and that's how that works.
For the cost analysis, we have done some due diligence on pothole filling robots, and we haven't found anything in comparison to what we have. The one that we have found is a large machine, which I will go a bit further into, but we did research on industrial type robots that have pretty similar functions, and it's estimated for all four to cost range from $100,000 to $170,000. For the market comparison and added value, the one that we have found is one large machine that does it all, but that doesn't do good for different types of terrain. Ours is more efficient as the division is all divided up between all four robots.
In summary, for the design in our engineering project, we found out that keeping things simple and practical was key. Even with just basic CAD skills, we managed to tackle challenges effectively by focusing on simplicity and functionality. For entrepreneurial mindset, in our business journey, knowing our market and what our customers really want was crucial. This understanding helped us figure out which features to focus on and how to use our resources wisely. As far as management, we got better at managing our projects by organizing schedules and dividing tasks efficiently. Good communication was key to keeping everyone on the same page and reaching our goals. For teamwork, we faced some hurdles, but by working together and helping each other out, we managed to overcome them and succeed. Things that we would do differently are additional AutoCAD training, more dedication to building and testing the prototypes, exploring project management tools to streamline the processes, and lastly, learn from the people that have already gone through this journey or that are already working in the robotics field. In summary, we created a cost-effective and human-safe pothole repair solution. It works through a swarm of 4 individual robots that perform very simple tasks. They're built with affordable materials that are easy to purchase and assemble, which allows for inexpensive and efficient manufacturing and repair. And of course, they were designed and envisioned by our team with the goal of adding value to the local communities worldwide. Thank you so much.